Now I am going to next video regarding the net question solutions of 2023. In this regards, we want to move to that of the pericyclic reactions related problem mainly. The pericyclic reaction, that is the two problems are giving in the pericyclic related, and one problem giving to that of the organometallic chemistry, and another problem is the heterocyclic chemistry. In the first problem is the dipolar cycloaddition using allyl silane. We know that the allyl silane is very reactive towards the different type of the electrophilic reactions. That is, the silicon can stabilize beta to the positive charge. That is, if the positive charge is created to the beta to the silicon atom, then it can be stabilized via the simple resonance, and hence this positive charge can be used for the cycloaddition reactions. Here, the mainly highly stabilized dipolar cycloaddition reactions will occur. In that case, the OTF is first split down, and the silicon gets stabilizes the allyl carbocation via the simple resonance effect, and hence it can undergo dipolar cycloaddition to give the dipolar cycloaddition product. That is, the OTF is first split down, and after the isomeric resonance to give the desired product. This is the one type of the 4+2 cycloaddition reaction, and the answer for the given problem is that 4. And this allyl silane is very much reactive towards the different type of the electrophiles. That is, the stereochemistry for the electrophilic addition to that of by the allyl silane is that the silicon is in the upside, and after the Cl minus add, it always go to that of the downside. That is, the silicon, the face of the silicon atom in the above side, but the electrophile is introduced in the below side. Here, the silicon stabilizes beta to the carbocation and produces the electrophile substituted asymmetric compound. And this allyl silane can be formed by the simple reaction with that of the trimethyl silyl methyl iodide with the Grignard reaction in the presence of the esters. By the excess Grignard addition, we get the tertiary substituted alcohol, and after the Petersson olefination, we know that the Petersson olefination means the hydroxy group and the silicon group in the beta position. It undergoes Petersson olefination by the simple cyclic additions, and to get the desired allyl silane product. And this actually reference is coming from that of the Claydon books, and so many interesting problem is given in the Claydon book. You see on the Claydon books on the silicon chemistry. Next is that dipolar cycloaddition is the one type of the dipolar cycloaddition simple by the elimination of the bromide by the using the zinc. Here the zinc has affinity to bromide minus and produces the carbocation, allylic carbocation, and then this allylic carbocation undergoes 4+2 cycloaddition reaction. The 4+2 cycloaddition means this is the 2 pi electron, and this is the 4 pi electron. This is one type of the dipolar cycloaddition reaction to get the desired cyclic ketone compounds. And another dipolar cycloaddition is that this is very interesting, and this problem is coming in the different type of the NET examination and also different type of the competitive examinations. Here, the dipolar, that is the dienophile, is produced by the simple from the alkyl nitro compound by the reaction of the phenyl isocyanide with the different alkyl nitro compound. And ethyl alkyl nitro compound is added to that of the phenyl isocyanide, and after the elimination of the alanine, the dipolar cycloaddition precursor, that is the dienophile, is produced, and this dienophile can add to that of the Z alkenes or the E alkenes, and the stereochemistry of the cis alkenes or the trans alkene after the cycloaddition reaction becomes written, and we get the cis substituted products and that of the trans substituted product. Here also this final product can be reduced to give that of the imine and the hydroxy derivatives by the presence of the hydrogen and nickel, and it undergoes hydrolyze. We know that the imines can be hydrolyzed to give the ketones and the hydroxy compound, and we get that of the alpha beta hydroxy ketone compound. And this beta hydroxy ketone compound can also be obtained by the simple aldol condensation reaction. But here the alkyl nitro can be converted to that of the beta hydroxy ketone by the simple cycloaddition reaction. Another problem is the regarding that of the stereochemistry on the nucleophilic addition. We know that the alkyl dialkyl copper lithium is known as the Gilman reagent, and this Gilman reagent has greater tendency for the 1,4 addition in case of the alpha beta unsaturated carbonyl compound, and it always prefer to attack that of the SN2 addition type. That is, the nucleophile is always approach backside to that of the leaving group. Here, with the given problem, the cyclohexene acetate derivatives, the alkyl group is added to that of the opposite phase to that of the acetate groups, and we get the cis substituted product. But this is very interesting to that of the different from that of the palladium chemistry. In the palladium chemistry, we see that if we get that of the allyl acetate, the palladium group is coordinated to that of the opposite phase of that of the X group. That is, the less sterically hindered side the palladium is coordinated, and the nucleophile is approaches back to that of the palladium and get that of the retention of configuration product. Here the nucleophile and the leaving group is in the retention of configuration product, but here the alkyl copper lithium, the inversion product will be obtained. And this is the main difference between that of the palladium chemistry with that of the palladium compounds with that of the alkyl dialkyl copper lithium compound. And this explanation is given actually here. The nucleophile is approaches at the same side to that of the leaving group. So the answer for the presence of the alkyl copper lithium, that the inversion product, that is the 3 is the answer. Next is the problem related to that of the cycloaddition and sigma-tropic reactions. We know that the cyclopentadiene has greater tendency for the 1,5 hydrogen shift. So in presence of the heat, it can undergo 1,5 hydrogen shift to give the proper dienophile, and then this dienophile can add to that of the this is the diene actually, and after 1,5 hydrogenation, this diene can add to that of the dienophile, and we get that of the desired product is. And the mechanistic observation for this reaction is that the first 1,5 hydrogen shift and then the 4+2 cycloaddition reaction, and we get that of the our desired product. So the option is that 1,5 hydrogen shift followed by 4+2 cycloaddition. And this problem is related to that of the 1,5 hydrogen shift. This is taken from the Fredon books. Actually, this is a highly strained ring, and it becomes readily eliminated to give the cyclopentadiene system. And this cyclopentadiene has greater tendency for the 1,5 hydrogen shift, and after the 1,5 hydrogen shift, we get mainly this product. But before 1,5 hydrogen shift, we did not get this product. But if we use the electron withdrawing group to that of the dienophile system, we know that if the electron withdrawing group in the dienophile is used, then the homolumo energy gap for the cycloaddition reaction becomes lower, and hence the cycloaddition reaction is more prominent. And for that case, in the presence of the methyl group, there has no cycloaddition reaction, but in the presence of the CO2Me group, electron withdrawing group, the before 1,5 hydrogen shift we get also this product, the highly complex molecules, and after 1,5 hydrogen shift we get that of the two product. But here only one product is obtained, but another product is not obtained. That is the before 1,5 hydrogen shift, this product is not obtained, but after 1,5 hydrogen shift, 1,5 hydrogen shift here is so fast, it can undergo cycloaddition reaction. After 1,5 hydrogen shift, we get that product. Next problem is that of the heterocyclic related problems. In the heterocyclic related problems, here the nitrogen lone pair is coordinated to that of the after conjugation. That we know that the indole is 3 position is more reactive compared to that of the 2 position, and 3 position is more reactive as if the 2 position is electrophile is attacked to that of 2 position, then the aromaticity is lost. So the indole cannot attack the electrophile at the 2 position like that of the pyrrole, but it can attack with the 3 position, and we get the 3 position substituted product. And after that, the indole, after another indole, can add to that of the hydroxy substituted, that is here a greater tendency for the SN to attack, and we get the desired product, that is the di-substituted indole derivative. And the option is that 1. That is, here the 2 substituted product is not formed, as the 2 substituted product is highly unstable due to the loss of aromaticity after conjugation. And this is the interesting problem. Here, the indole containing the electrophilic substitution reaction on the indole, if the sodium hydride is used, then the nitrogen atom of the hydrogen atom on the nitrogen is deprotonated to produces the localized negative charge, and this localized negative charge is attacked by the methyl. We get that of the N-methyl indole. And if the magnesium is used, in presence of the sodium hydride, we get this N-methyl indole, but in presence of the magnesium, the electrophile is attacked to that of the 3 position, as like that of the other electrophile, and we get the 3 substituted indole. And if the N-methyl is blocked, and if we get that of the N-butyl lithium, then the negative charge is created ortho to that of the nitrogen, that is C2 position, and negative charge is created here, and the electrophile is quenched by the epoxide. We get this product, and this observation is obtained by the different type of the electrophilic addition or the nucleophilic addition on the indole derivative. In the upcoming video, we will discuss the following problems. Thank you for watching the